back, and we are very happy to have Thibault Décoppet who will tell us about the classification of fusion group applications.
First of all, thank you so much for the invitation. It was a bit of a struggle to come here, but the views and everything are really worth it. And then this project is still ongoing, so some details might change, but probably not that much. And it's going well with Huston, Johnson-Freyd, Nikshych, Plavnik, Reutter, and you. Well, it's kind of, yes. And also something that's going to be important for this talk, and was, I guess, important for, most talks today, is that I'm going to work over the as ultimately closed and in fact as zero. And just so that David already told us the definition before, but let me just for emphasis, those are the things that I'm actually, I will tell you how to classify shortly, so we might as well have the definition. So fusion two-category is a finite simple rigid monoidal two-category with a simple monoidal unit. So I'm going to use I for my monoidal unit, and as David very rightfully pointed out, what's difficult to make sense of in this definition is what it means for a two-category to be finite simple, and it's something that Douglas and Reutter did some time ago. The details of what this means are not going to be terribly important for us, but I'm going to highlight a few key properties. One of them being that if you pick any object of your fusion two category, there's an associated monoidal one category endomorphisms, and all of these are multi-fusion one categories. So multi-fusion means that the monoidal unit doesn't have to be a simple object. Kind of like you can think of, if you like, finite and simple algebra, like the difference between a field and a matrix. And in particular, an object is called simple if its endomorphism, the multi-fusion category is actually fusion, meaning that the monoidal unit is a simple object. And one fusion category that's going to be very important for us today is this omega C, or loops of C, if you think in terms of, if you think homotopy theoretically, this is loops of C, which is the braided fusion one category of endomorphisms of the monoidal unit, and it is it's braided by some kind of usual Ekman-Hilton algorithms. Something that I have to point out, and that is really in terms of like how you approach this object, the main difference with how you would approach the theory of fusion one category is that the Schur lemma doesn't hold anymore. I will have an example shortly, but what I mean by that is that now you can have, so in the fusion two category, or more generally in the finite and the simple two category, you can have two simple objects that are not equivalent, but yet between which there exists a non-zero one morphism. And in particular, this makes the following notion into something that's actually interesting and quite relevant, the notion of a connected component, which is that you can now say that two simple objects are connected if you can go from one to the other by a non-zero one morphism. And this defines an equivalence relation. You can check that, and then this gives you I0 of C, which is finite system connected. Any first part questions? Some examples. I mean, they're really the examples that David gave, but for the sake of emphasis, I guess trivial or fundamental example is this to having two vectors of finite and simple one category. You can, so if you know about fusion one category, something that's very that's a construction that's very elementary is to look at G-graded vector spaces. So here we can look at G-graded two vector spaces. And in this case, the simple objects are given in correspondence with the elements of the groups, and they multiply exactly. The multiplication between them is given by the multiplication of the group. And in fact, you can twist this construction a little bit using a four cycle for loop. And by twist, I mean you can change the complete, like slightly different things later of the monoidal category. There's also kind of dual construction. You can look at two representations for your group G, or maybe I should say finite semi-simple two representations. So by that, I mean it's more or less, so by two representations, I mean it's a two vector space, so meaning it's a finite semi-simple one category with the G action. And these things also form a fusion two category. because we are working at the two categorical level, we are actually allowed to work with two groups, or maybe categorical groups, or people in the audience level. I'm trying to think of two groups as something slightly different and not like a categorical. And another class of fusion two category that is fairly easy to describe is the ones that are associated with a braided fusion one category. Namely, if you give me a braided fusion one category, I can look at this fusion two category mode B of finite semi-simple B module one category, and it has a monoidal product thanks to the relative ability of the product that Christoph talked about this morning. And here I'm really using the fact that B is braided, so my B is not braided. This doesn't make sense. Yes, and you can check that these fusion two categories are exactly the ones that are connected, meaning those are exactly the ones that have only one connected component. And in particular, they are completely determined by the loops, by this expression omega. Namely, if I have omega of 1b, I just recover b.
When you say these, you mean just the last one? Or?
Yes, just the last. Yes, yes. So yes, it's a good point. So so the connected components of 2 G are just given by the group G. And then in the two group K, it gets more annoying. So let's not get into that. But yes, the point is they are non-connected fusion two categories. A concrete example. I don't want to explain too much what it is, but I think it's just interesting to kind of look at some pieces of data associated with one specific example. So on the left, you have a little diagram that kind of depicts the underlying finite semi-simple two category. So the vertices correspond to the 4 equivalence classes of simple objects. And then the edges give you the non-zero categories of endomorphisms. And in particular, you will see that between I and X, there are many non-zero one morphisms, which is what is telling you that the full lemma doesn't hold. And then on the right side, we have a table with the fusion rule, which if you work with fusion one category long enough, you will realize cannot possibly be the fusion rule of any fusion one category. And now, because not everyone in this audience is familiar with fusion one categories, I kind of felt like I had a duty to tell you why the classification is, well, why it is surprising and why it is not at the same time. So what I mean by that is that I'm going to propose an AND that I suspect that it might be possible to make it into an actual theorem, some flavor of another, but I don't know. In any case, as a kind of like postulation, you should think that the classification of fusion one categories is very, very difficult, and in particular is much, much more difficult than the classification of finite groups. And the classification of finite groups is really difficult, but my base is like going to be how hard are you from the classification of finite groups. And some heuristic for this postulation is that there are many fusion one categories that are not group theoretical. So in particular, you can construct fusion one categories from groups of vertex operator algebra, so really from least theoretical representation data. And in fact, you can even construct some fusion categories using what are called subfactors, which are objects that show up in functional analysis. So really things that are really quite exotic and very far away from anything that has to do with finite groups. On the other hand, we have the following result, namely that every fusion two categories is Morita equivalent to a connected one. And it's kind of really the basis for this whole classification, as I'm hoping to be able to say a little bit more later on, because it gives you, if you think how not, but this data gives you a good handle on the Morita classes of the fusion two categories, and once you've understood the Morita equivalence classes, then there is some hope to like reconstruct every element in any single Morita class. some comments for it older now, that the decategorified version of this statement is essentially completely meaningless because there's only one connected fusion, one category is vect, and the only fusion category that is Morita equivalent to vect is just vect itself. So really, it's like really a new phenomenon. And the other one is that even if you try to classify fusion one category up to Morita equivalence, that might seem like a good idea. It's essentially as hard as just classifying fusion one categories by themselves. We did actually learn a lot more fusion two categories. They're much more easy to classify to Morita equivalent than they are. That's quite good. Okay. Maybe any questions at this point? No. Now I just have one slide with the definitions. Just wanted to make sure that I could not lose everyone that didn't already know these definitions. If you have a braided fusion one category with some braided beta, there's a notion of a transparent object. And an object B is going to be transparent if it double braids trivially with any other object in the braided fusion category. It's some kind of center, it's some kind of like, trying to detect whether an element is center. That's how you should think about this. And in fact, there is a corresponding center light notation for the subcategory of these objects, this Z2 of B. And it turns out that the Z2 of B now is a symmetric fusion one category. Shouldn't come that much as a surprise because, again, some kind of center construction. And it's still fusion. And a class of braided fusion one category that anyone that's interested in topology, I'm sure has already come across, are those that are so-called non-degenerate, meaning that this center is actually very trivial. It's as small as it can be. It's just the category of finite dimensional vector spaces. So if any of you has heard the name of a modular tensor category, like in particular, any modular tensor category will give you a braided fusion one category that is non-degenerate. And now the relevant notion at the level of fusion two categories. So it turns out that for a lot of purposes, in particular for the purposes of this classification that's going to come up, it's convenient to split the classical fusion two categories into two pieces, into the bosonic ones and the fermionic ones. And well, the definition is a bit requires this Z2 center. And so the fusion two category I will call it bosonic if. So remember, groups of C, this is now a braided fusion one category. And in particular, I can take its symmetric center as in this definition above. So now I have a symmetric fusion one category. And it turns out that symmetric fusion categories by the theorem of Deligne are either Plavnik, meaning they are equivalent to rep H for some finite group H, or they are not Plavnik. And C is bosonic if this thing is Plavnik. And otherwise, it's called fermionic. And the classification in the bosonic version, so I'm going to state it first because it's a bit easier, and I will show you the fermionic version quite a bit later on. I feel like I'm doing. So the classification of bosonic fusion two categories proceeds as follows. So the first piece of data is a non-degenerate braided fusion one category A. So maybe remark I should make here, in particular, because we know that fusion two categories in particular contain all connected fusion two categories, they should at least contain all braided fusion one categories, or at least the one that are that have the Z2 being Plavnik. So this is more or less something that we expect. It's also telling you that the classification can only be as good as the classification of some flavor of braided fusion one categories anyways. So I think something I should point out is that by classification, I mean classification up to some data that's already known. And one of these pieces of data I'm going to assume is that we know a lot about non-degenerate braided fusion one categories. Another piece of data is going to be an inclusion of finite groups. And then we're going to have an action of H on A by braided monoidal equivalences, and then some homotopy theoretic data, so a focal cycle for G, and then some kind of like homotopy between pi of H and A. So the last piece of data I don't want to spend too much time on. The comment is for experts that will hopefully understand what I mean by that. It can seem like it's quite a lot, and it's non-negligible, but it's also, in some sense, surprisingly small. And in any case, if you don't want to remember all of that, what I think you should remember is that fusion two categories are, in some sense, braided fusion one category and group-theoretical. Anyways, that was kind of a sentence, so try that again. What I think you should remember is that every fusion two category can be constructed from the data of braided fusion categories and group theory. So braided fusion category comes up in 1 and 3, I guess, and then group theory is 2, 4, and 5. Where by group theory, I mean you just mean the low dimensional homotopy theory or something. And I think, when you just look at this, it's sort of hard to understand where some or maybe even any of these pieces of data actually come up when you try to reconstruct the corresponding fusion two category. So let's do a few examples. So one example that is interesting to look at is if the inclusion of finite group is just an equality. And in this case, it turns out that a whole bunch of things are actually determined. So well, you can still choose A. Then we have fixed the inclusion. So then essentially we just have this choice of the action of G on A, because essentially 4 and 5 cancel each other out. And the fusion two category that you reconstruct is this mod of AG, where AG is the notation for the equivalentization of A under G, or if you come from a more homotopy theoretic background, it's the homotopy fixed points of A under the action of G. And what this tells us is that with H equals G, we just get all bosonic connected fusion two categories. So that's good. That's one of the classes that appeared before. One can also take H to be the trivial subgroup, in which case we get something that's completely orthogonal. Namely, we get all the fusion two categories that are in some sense maximally disconnected. So namely, there's some tensor product of mod A and 2 vec G twisted phi. And some case that is essentially different from those is when we fix A to be as trivial as possible. So we can take A to be our favorite non-degenerate braided fusion category just vect. And in this case, it's about to just recover the group theoretical fusion two categories. And in particular, some examples that we've seen before, this 2 rep G just corresponds to then also taking H to be equal to G. And this weird thing that was the example that I unfolded explicitly corresponds to the inclusion of Z2 into A4. And something that I wanted to point out is that more generally, since this is kind of slightly generalizing the first point on top, is that you always have that group sub C is going to be given by the equivalentization of A by H, because in the classification, you have this A and you have an action of H on A, so you can always define this A over H. And in particular, group sub C is something that's like very easy to read off on the Fourier classification. Are there any questions? I'm just going to flag it. I'm not going to go over it again. But there is a corresponding Fermionic version where essentially you just need to put super everywhere. It's deceptively, it is very deceptive to say that it's just putting super in front of everything, because it turns out it's quite a bit more subtle. The bosonic version is really quite a bit easier to establish than this version. But at least morally, you just put super in front of everything and everything still works. Though in practice, it's hardly that. Because I've been very fast, I guess I do get to talk a little bit about the proof. I'm not going to get into any kind of really gory detail whatsoever. I just wanted to point out one result that comes into the proof that I really like, But it does require to introduce a little bit of background. So I hopefully motivated earlier on that the classification of fusion to categories essentially can proceed by the fact that we understand the classification of two Morita equivalents. And what do I mean by that? Well, one thing that one can consider is this category. I decided to name it all back for reasons that I'm happy to tell you in a private discussion. But this is my notation for the symmetric monoidal Morita category of fusion to categories. So this is some a big, like a big higher category where objects are fusion to categories. One morphisms are nice enough by modules, and then you continue the quote-unquote obvious way. This is one very non-standard way of defining the Witt group, well, really Witt space, because now that I have some kind of higher category, I can take its Picard space or Picard spectrum, which is you just remember the objects and the morphisms that are invertible. And this gives you Witt, but I really want to remember this Witt of vect. And now this is a space that has some homotopy groups that are understood. Huston remark. So please come, if you're interested by this remark, please come talk to me. I think it's quite fun. I like talking about this a lot. Is the fact that this space, Witt vect, you should really think of it as some kind of higher broad group associated to the fusion to category vect. But it's a bit of ornament to my point right now, so let me go through it quickly. What's more relevant to my point is that, in fact, you can perform a similar kind of construction for any symmetric fusion one category E. So you can define Witt of E for any symmetric fusion one category. Essential stuff. You can replace vect by a general symmetric fusion one category. This gives you, again, some kind of space Witt E. And why are those spaces relevant? Well, it's because the collection of all of the spaces for E varying actually are very closely related to the space of Morita equivalence classes of fusion to category. And not exactly the same generation. And this is very good because by the Lee's theorem, you actually understand symmetric fusion one category very well. They're either representation of a finite group or representation of a finite pseudogroup. And the theorem that I really, really like, that is kind of like goes into the proof of the classification is this statement. So it's the statement that, well, first of all, this construction which actually defines a functor from the two category of symmetric fusion one categories and symmetric monoidal functors into the, I guess, infinity category spaces, where you send the symmetric fusion one category to this space with E. And then what is really interesting is that this functor actually preserves equivalentization, or really, for the homotopy theorists, it preserves homotopy fixed points for actions by finite groups. And this is really important because all symmetric fusion one categories are actually equivalentization of either vect or supervect by a finite group. And so this gives you like a tremendous amount of control on these spaces with E, and again, by the remark just on top, this should kind of make you sense that this plays like a role in the classification that is non-rigid. Any question? Well, because I have a little bit of time, I also do like the statement because it's some kind of Galois homology statement. Oh, it's reminiscent of statements that are familiar with the world of Galois. Anyways, what are some applications of this classification? Well, there's a bunch of results that are very familiar with the theory of fusion one categories that were not known for fusion two categories, but are now very easy. Because if you have a classification where you can just essentially check that every example satisfies, like, behaves the way you expect. One of those is so-called rank finiteness. So you can define the rank of a fusion two category In this case, you have to take into account the number of connected components and the rank of loops. So where the rank of a fusion 1 category is the number of simple objects. So in particular, it just follows from the classification that there are only finitely many fusion 2 categories in a given round. Another statement that's very familiar in the theory of fusion 1 categories is Ocneanu rigidity, the fact that fusion 1 categories have no non-trivial deformation, that fusion 1 categories never come in like infinite families. This you can also read very easily in the classification for 2 categories. And I should say it's kind of, you can try to do Ocneanu rigidity kind of like without going through this, but I've never been able to make this work somehow. The only way I know how to prove Ocneanu rigidity for fusion 2 categories is by the classification. And another corollary, I'm going to focus on the second part of the collision more to talk about hypergroups. But it's the fact that essentially the fusion ring of your fusion 2 category is essentially one of those, given one of those double coset hypergroups. But really concretely in terms of connected components, it tells you that the set of connected components of your fusion 2 category is given by one of those double cosets, where H and G are the H and G's that appear in the classification. Which is, again, something that seems very reasonable, but I have no idea how to prove without appealing to the classification. Thank you very much.
Questions?
The conditions are the data that you gave us, and which conditions do those actually give you the same categories?
Yes, it's a good point. So for 1, 2, and well, 2 is purposefully stated in a certain-handed way, meaning that you, depending, yes, I think it's something that you have to. Essentially, it's unique if you think of them in the right way. It's very misleading. What is slightly misleading is that we're essentially describing the space of all the fusion 2 categories, and then it becomes a bit clearer. But in particular, if you look at point 2, by an inclusion of finite groups, I mean 2 subgroups that are conjugate are going to give you the same inclusion up to conjugation in the target, and so I want to think of them as being the same. And that's the kind of thing that you have just essentially put it out by in this list.
Do you have any examples of when you can compute these web spaces in the way like in general, like homotopy or anything like that?
It has been a problem in the field for a long time. So it's very interesting. The width of vex, the structure of width of vex is now as a group. So sorry. So that width of vex has exactly 2 non-zero homotopy groups. One of them is just the units in your field, so it's uninteresting. The other one is very interesting and is actually completely known as an abstract group. Well, I mean, it's infinite, whatever, but I was completing fairly recently, and the proof of the structure of this group actually used fusion 2 categories. It's still a big problem in the field to actually find, give explicit generators for this group. Perry is the leading expert on this endeavor, but it's proving to be very difficult. Now, essentially, thanks to this statement, at least in the bosonic case, it's really fairly easy to then understand what the corresponding widths are. At least you understand them as much as you understand width effects. In the fermionic case, it's not so true because the width of this vector has essentially, I think, 4 or 5 non-zero homotopy groups. So you have a spectral sequence, but I don't really know how to deal with it. So yes, in the fermionic case, I think there's still work to be done to really understand those spaces.
Can you explain again how you construct the implementary of your data?
Yes, you can do it.
Is it like category of modules of prioritization?
So roughly,
You're talking about the precision, right?
Mm,
It's also really better.
So essentially, what you do, okay, it's terrible that I don't know functor, but essentially what you do is you construct a nice algebra in 2 vector pi g times mod a. And then you take binomials for this algebra instead of this. That's
And your data, you visit your data, right? It allows you to construct.
yeah, it allows you to construct this and an algebra instead of it, and then you take binomials for all.
Okay.
So in the one fusion category, if I take something like G omega, there is a very nice classification of model categories of it.
Yes.
In the 2 fusion category case, do you have such a classification for some type of model categories of the 2 vector G?
I mean, yes, but they're always very big and infinite, and therefore, not so nice. I mean, for 2 vector G, we basically just have all G braided fusion categories. Yes, you always get it. But even for 2 vector, it appeared in David Stokes. The nice module 2 categories for 2 vector is given by mod of any fusion 1 category. And in some sense, this is exactly why fusion 2 categories up to Morita equivalence is manageable. It's because, well, there are many things I identified up to Morita equivalence. Unlike in the case of fusion 1 categories where very few things are.